Okay, this is the lesson for Unit 4.2 about particle motion. Previously, we learned about taking derivatives in context, and now we're going to learn about velocity, speed, and acceleration and how they relate to derivatives. Okay, so first things first, our position function is usually denoted with s of t. And again, that's just your position on a graph. If you take its derivative, you get velocity. So the derivative of position is velocity. And then acceleration is the derivative of velocity, which is also the second derivative of position. Now, what is the difference between speed and velocity? Not much. The only difference, at least in physics, is that velocity has a direction. So you could be traveling 70 miles an hour. That's just a pure speed. But if you're going 70 miles an hour north, that is a velocity. And we denote it this way, where we take the absolute value of velocity, and that's speed. So it doesn't matter if your velocity is positive or negative. If you just take the absolute value, that's speed. Scalar is just a number, right? This is just a number, but if it has a direction, it is now a velocity. And then just a few notes that all motion is rectilinear, which just means it goes in a single direction, horizontal or vertically, usually. Okay, so here, when you're reading these types of problems, I tried to make this chart for it so you can break it down a little easier. So if the bug is stopped, that's the velocity equaling 0, right? And if you want to solve that, you just solve for t after you set velocity equal to 0. So that's whenever you hear something like the object has stopped. If you're moving to the right, that means the velocity is greater than 0. And then if you're moving left, that's the velocity is less than 0. If you were trying to solve this with an equation, you would have to set your velocity equal to 0 and then use a sign chart to see if it's moving left or right. If the object turns around, that means you change from positive to negative or vice versa. So you just have to figure out where you change sign. And again, you solve this using a sign chart. And the difficult ones for at least students and other people to remember is when you're talking about speeding up, your velocity and acceleration have to be in the same direction. If you are slowing down, your velocity and acceleration are in opposite directions or have different signs. And I guess the best way to kind of denote this is if, your velocity is going this way, but your acceleration is decreasing, then you would be slowing down. And then if your velocity is going to the right and your acceleration is going to the right, you're speeding up. So I guess that's the kind of best way to kind of think about it. All right, let's look at example 1. So we have for time from 0 to 8, a bug is moving on a line in the x direction. It gives us this equation. And again, this is going to be the position equation. So what position of the bug when he first starts walking? So that's at time equals 0. So if I plug in 0 into my equation, you're just going to get 2. Because you are plugging in time equals 0 here, here, and here, and those go away, and you're just left with 2. So that's, again, his initial condition, their initial condition. So next part, what happens, or what time is the bug stopped? So you are looking for the derivative equaling 0. So let's take the derivative. So the derivative of the function. So again, we're going to take each of these derivatives separately. So the 3 is going to go down and multiply to the front, and then you're going to subtract 1 from the 3. The 2 is going to go down outside, multiply, and then subtract 1. The derivative of 12t is just 12, and the derivative here is 0. Okay, so if I clean this up, these 3's cancel, so we're left with t squared. These 2's cancel, so we're left with minus 7t to the first, and then 12 plus 0 is 12. So from here, set this equal to 0 and solve. If I factor, I'm going to get t minus 3 times t minus 4 equals 0. So this means that we have 2 times the bug is stopped, and that's at 3 and 4 seconds. And then part C is when is the bug walking to the left? So we're going to do a sign chart, and we're going to plug in different values. So I guess we'll plug in 0, we'll plug in 3.5, and we'll plug in 10. And we are plugging this into the derivative. So let's note that over here. Okay, so if I plug in 0 here and here, I'm going to get 2 negatives, which makes a positive. If I substitute 3.5 into here, I'm going to get a positive number. And if I plug in 3.5 here, I get a negative. And that equals a negative. And then if I plug in a 10, I'm going to get 7, which is positive, times 6. So those are 2 positives, and I get a positive. So the bug is moving left between 3 and 4 seconds. Example 2. The graph below models the velocity of a bug on the interval from 0 to 13. So let's note that this is the velocity function, v of t. Now, part A says find the velocity at 3 and 11. So for that, that's simple. Just look at 3, go up here. So we got 6. And then at 11, we're at -1. Part B says find the acceleration at those 3 values. And again, remember that acceleration is equal to the derivative of the velocity. So we need to find the slope of the graph at those points. So if we go over to 1, it looks like the slope of this line is 2. If we go over to 5, which is here, go up, the slope there is 0. And if we go to 9, the slope here is going to be -2. Question C, it says, at what time does the bug turn around? Give a reason for your answer. So again, when you turn around, you're looking for the velocity changing signs. So the velocity is positive here and then turns into negative. So it looks like at t equals 9, we change directions. And so you would say the bug turns around at t equals 9 because the velocity changes sign, positive to negative. D, on what interval does the bug have a negative acceleration? So the acceleration is the derivative of velocity, and we want that to be negative. So if the velocity is negative, or I'm sorry, if the derivative of the velocity is negative, which means your slope has to be negative. That's what the derivative of the velocity being negative is. It means you're decreasing. So if we look at the function, we are decreasing from 6 to 10. So my velocity is going down, the function's going down, the slope is negative, the velocity is decreasing, all the same things. And then how many times is the speed of the bug equal to? So again, speed is the absolute value of velocity being 2. So that means either you need it to equal 2 or -2. So if we come over here and look at our graph at 2, it looks like that is at time equals 10. And then positive 2 is at 1 and 8. So that is 3 times. Number 3. This does say calculator active, so you do need your calculator. So from 0 to 2, a bug is moving along the x-axis with the velocity function given there. And then it says find the acceleration at at t equals 0.7. Is the bug speeding up or slowing down? So looking at this problem, acceleration is the derivative of velocity, and we need to plug that in for 0.7. So we need to take the derivative here and then find the answer at 0.7. So we're going to go to our graphing calculator. Okay, so if you open up your calculator, you're going to go to y equals. We're going to type in this equation. We're going to use x instead of t. And then after you input your equation, make sure you always hit enter so it locks it in. Now notice mine is in y1, so I'm going to quit out. Go to the derivative, which I hit math. That's number 8. Mine was at y1, so I have to go to variables, go to y variables, functions, y1, and then I need to plug in 0.7. And so I get that my derivative is negative 9.2055. Okay, so we found that part. Now it does say, is the bug speeding up or slowing down? So we need to check it with velocity. So the velocity at 0.7. And again, we can just come over here to the function. At 0.7, it looks like we're here. We're negative. That looks to be about negative 0.3-ish. And again, we could technically find it if you just plug in 0.7 into here, here, and here. But we just need to see if it's positive or negative. So it is negative. So the velocity and the acceleration have different signs. I'm sorry, the same sign because they're both negative. So we say the bug is speeding up. And it's speeding up because both values are negative. Okay, part B. Find any values in the interval where the bug is at rest. So the bug is at rest when the velocity is equal to 0. So if we come over here, it looks like it's going to be here and here. Now let's go find those values on the graphing calculator. Again, so I have my function. Let's hit graph. My window is really messed up. So if I go to window, zoom. And then I go to standard, which is number 6. It looks like this graph is a harmonic frequency, but we won't worry about that. Let's just zoom in here. And again, if you need to figure out how to do that, you can go to zoom and then go to square, which is number 5. Sorry. Go to zoom and not that one. It is okay. I think you should have a zoom box. Zoom in with you can make a box where you want to zoom in. I think it's because I'm using my iPad. I don't have it, but we'll make do. So anyway, I want to find basically my intercepts, and you can see if you kind of trace. You can, but you can calculate these if you go to calculate, which is second trace, and then it's the 0 button, and it needs to know the left and right bound. So let's go left of the x-intercept, right of the x-intercept, and it does say that the 0 is at 1.22474, and if I did that same thing here and here, I get 1.80711. All right, part C. It says find the open intervals where the particle is moving to the right. So we want the velocity being greater than 0. And we can kind of see on our graph that we're greater than 0 from here to here. And those were actually the intercepts we found, right? Because this value is 1.2 and this value is 1.8. So we're moving to the right here, and this part is moving to the left, and also this part's moving to the left because it's negative. Okay, now part D, find the acceleration of the bug when the velocity is equal to -1. So -1, we need to find this value here. And then we need to plug it in. We need to find the derivative there. So we need to find t first, and then find the acceleration at that value of t. So going back to my graphing calculator, we're going to kind of do a trick here. We're going to plug in -1 as another function. Go back to our graph. And we see that we can see that it intersects there. Now, to find that value, again, we're going to go to second calculate or second trace, and then intersect is number 5. So we're going to go left bound, so go to the left of the value, go to the right of the value, hit enter. And the intersection, it shows you right there. It's really small, but it says that it's 1.8368. Now, we just need to find the derivative at that value and go back. I'm going to go and delete this. So again, derivative is just another calculate, so it's going to be second trace again. Derivative is number 6. And then you're just going to type in that 1.8368. And then it tells me the slope of the tangent line right there is -28.8724224. Example 4. For t equals 0 to 8 seconds, a particle moves along the x-axis. The position, velocity, and acceleration are differentiable and modeled by the functions x, v, and a respectively. The selected values are shown in the table below, measured in units. So differentiable just means that we could take the derivative. There's no discontinuities anywhere. So question A says, is the particle moving away or towards the origin at time equals 4? Give a reason for your answer. So let's look at 4. Let's see what this is. So it looks like we need to figure out where we are starting and where we are going. So if this is the origin at 0, it looks like my starting position at 4 is 6. So the particle is starting here at 6. Now, let's look at its velocity. Remember, positive means moving away, negative means moving towards. And if we can see here, the velocity is -1, so we are moving toward the origin. So, and the way you would explain this, you would say at the position at 4 is equal 6, and the velocity at 4 is -1, which means it's moving left. Again, I don't know if I said that correctly. Positive means you're moving to the right. Negative means you're moving to the left. So There you go. Part B. Is particle P speeding up or slowing down at time equals 7? So let's look at time equals 7. And let's try to analyze what's going on. So again, speeding up or slowing down means that either the velocity and the acceleration are the same sign or they're different signs. So if we notice here that they're both the same sign, so that means we are speeding up. And if you wanted to argue, you can just say the velocity and the acceleration at that point are the same sign. So they're, in this case, they're both less than 0, which means they have the same sign. C, it says use the data in the table to approximate the position, the velocity at 2, indicate your units of measure. So when it says approximate, that's the previous lesson. We are going to use our average rate of change at 2. So we are trying to figure out the velocity. So we're going to use these two values and guesstimate using average rate of change. So we're going to have 8 minus 2, which is 6, over 3 minus 1, which is 2. And then the values are going to be meters per second, because look, we're in meters, and then per time, which is seconds. Question D, is there a time C from between 1 and 7 such that the velocity equals 0? Justify your answer. So this is going back to one of those existence theorems. So between 1 and 7, is the velocity equal to 0? So from here, sorry. Let's look at these values. So from 1 to 7, do we equal 0 somewhere? And the answer is yes, because look, this is going down, and it gets to negative at some point, so it has to pass through 0 to get to the negative, and it's because it's continuous, which is implied with the differentiable. So that was like a necessary requirement. So yes, by the IVT, intermediate value theorem. So you would say the interval 3, 4 is part of the interval 1, 7. And since it's differentiable, it is continuous. And then you would say the intermediate value theorem guarantees that there exists a C such that C is between 1 and 7, where the value at C equals 0, because 0 is in between 5 and negative 4. Question E. For time 5 to 8, a second particle moves along the same axes. The position of particle Q is modeled by that function at time equals 7. The particles P and Q are they moving towards or away from each other? Explain your reasoning. So to answer this question, let's look for the original first. So at 7, let's see what's going on with this function first. So notice that it starts at 5 and it's moving to the left. Okay, so let's just state that explicitly on our notes. And again, this is at 7 seconds. So let's do the same thing for x of q now. So let's find its starting position at 7. So we're going to start its starting position. We're going to plug in 7 into the equation. If I solve this, I'm going to get that it equals 3. So this is x of q. Now we need to take its derivative, x prime of q, and we need to see which way it's moving. Is it moving to the left or right? So taking its derivative, I'm going to get 0 here minus, and then again, we're going to do the chain rule, so that's going to come out as a 2, t minus 10. And then we do have to do the chain rule here. The derivative of t minus 10 is 1. So it looks like this is going to be negative 2t plus 20. And then we need to figure out what's going on at 7. This is negative 2 times 7 plus 20, negative 14 plus 20, which is 6. So this is moving right. So it looks like the particles are moving towards each other.